this will be another problems of optimization problems. So then the question saying that, okay, this is a diagram given. So the question saying that the diagram shows the cross section of a solid that consists of a cylinder of radius r surmounted by a hemisphere. Means that this will be a cross section area for cylinder, and this will be the cross section for hemisphere, right? Which is surmounted, which is exactly fit the cylinder here. So the volume of the cylinder, alright, only given that the volume of the cylinder, okay, as you know that you can redraw this as a 3-dimension. So where there is a cylinder, right, there is a cylinder with height h and radius r, right, according to here, the cross section r, and there is a hemisphere on top here, right, and the hemisphere of course will be also radius of r because it's surmounted with the cylinder. All right, so given that the volume of the cylinder is fixed, they fix the volume of the cylinder, so it means that the volume of the cylinder, right, the volume of the cylinder, I write as VC, which is 192 pi centimeter cube. Okay, 192 pi. So this is given. What is given? Show that the question is asking you to show that the total surface area of the solid, right? The total surface area of the solid is given by A. Okay, given means that they show that the total surface area. Okay, so A is 3 pi r to the power of 2 plus width 384 pi r, right? So pi over r. So you have 384 pi over with r. Okay, this they're asking to show that the surface area. As you know that the surface area of this is consists of the surface area for the hemisphere and the surface area of the cylinder. But you have to remember this is not counted. It's not counted because why? It's inside. It's not outside. Surface area is something that you can touch from the outside. So then the surface area here, okay, I'm going to list out what is the surface area here. First for the hemisphere, right? For the hemisphere. So the surface area for hemisphere will be 2 pi r squared. Alright? 2 pi r squared. So it's only outside here. Means that the sphere, alright? Not this pi r square is not included. Pi r square, right? It's only 2 pi r square. And of course the side here, okay, as if you open up this thing, it will be look like a rectangle for the cylinder. If you open up the cylinder, you will see that the open surface here, you will see that this is your height h, right? Your h, and this one, the circumference of the length of the circumference of the circle will become the become the side, the length, the height here, and the length for the rectangle here. As you fold this thing, you fold it out, you will get a cylinder, right? So what is this? This is circumference of the circle. So it will be r, right? So the formula for circumference will be 2 pi r, right? 2 pi, the length here, 2 pi r. So it means that the surface area for the curve here, right? The curvature of the cylinder will be h multiply 2 pi r, which will be plus with 2 pi r h. So you have the second one. First, the hemisphere, 2 pi r squared. Second, this one, the curve, alright? So the round surface of the cylinder. And the bottom, right? The bottom thin. So here you have pi r squared. So you have to add pi r squared, the area for circle, pi r squared. So if you total up, you have A equals to 3 pi r squared, right? 2 pi r squared, plus with 2 pi r h. So then you are getting the surface area formula for this solid here. So next, they already given that, but the problem is if you want to find the minimum area, the minimum surface area, Alright, you have to write this function in terms of only one variable here, because r is changing, right? R is the unknown, and h also an unknown. H is changing, r is changing, right? So you cannot differentiate something with respect to two variable. Alright, so we have to replace somewhere. So as you see that they're asking you to proving that a is 3 pi r squared plus with 384 pi over r. There are no h inside here. Means that the h here you're going to replace with r. So you have to find the relationship between h and r. So as you know that it's already given that the volume of the cylinder is the volume for solid cylinder, the formula is pi r square h, right? You're very familiar with this formula. Pi r square h is the volume of the cylinder, so which is equals to 192 pi. This is important, right? So this is a fixed, this is fixed, okay? The volume is fixed, just the r and h is changing. So then you have divide pi both sides, then you have h equals to 192 over r square. This is an important relationship that you found. So then you're going to replace this into the expression here. So 2 pi r h, your h will be 192 over r to the power of 2, and a will be 3 pi r squared plus with r and r cancel off, f 2 times 2, 4, 2, 19, 38, 384, right? 384 pi over r, which you already proved, right? You already shown. So you have shown that this will be the formula, right? This is a model, means that the area is related to radius by this equation, right? By this equation here. This is not a polynomial equation, all right? This is not a polynomial equation. So, all right, later the question is asking you to find the maximum volume of find the maximum value of the total surface of the solid. Means that they want to find the maximum surface area here, right? The maximum surface area here. So to find maximum or minimum is referred to optimization problem or relative extremum problem, right? Relative extremum problem. So now you want to find maximum or minimum, you have to find the stationary point for this equation here. So let's see how to find the stationary point. Alright, sorry, the question is want you to find the minimum surface area. Alright, I have wrongly mentioned just now is to find the minimum value of the total surface area. Alright, so you have to either you are finding minimum or maximum, you have to differentiate this to find the stationary point. So, okay, for minimum to occur or optimum value to occur, so you have to find the dA dr. So 3 pi r power of 2 plus with 384 pi r to the power of negative 1, right? R power 1. So differentiate dA dr. So you're getting 6 pi r, right? 6 pi r minus with 384, 6 pi r negative basic rule 384 pi r to the power of negative 2, right? So which is r to the power of 2. Alright, so usually I will ask students to differentiate for the second derivative so that we can using this to verify that there is a maximum or minimum point here. So differentiate this for one more time, you have 6 pi, right? Constant, and r is like something like x. So then you plus with 2 times with 384, right? 2 times with 384. So 2 times with 384, you have 768, right? 768 pi over r to the power 3. Okay, this one you were using later for your second derivative test here. So, but now you want to find the optimum value, either maximum or minimum value, you have to taking the dA dr equate to 0, right? Means that this to be equal to 0. 6 pi r minus with 384 pi over r square equals to 0. Because you want to find the value of r, right? The value of r such that the surface area is minimum, right? So usually surface area we want to find for minimum surface area because it's a costing, right? The smaller the surface area, the lesser the material used to build that box, right? That container. So then you multiply, I think, with r square, you have 6 pi r cube minus with 384 pi equal to 0. So then you can divide both by 6, I think, 64. So you have 6, divide by 6 pi, alright? Divide by 6 pi, the equation, everything divided by 6 pi. So you are getting r cube minus with pi 64 equal to 0. So means that there is only one value of r, right? So r cube will be 64. So r must be 4, right? Because 4 power of 3 is 64. So then if you verify, if you see that your second derivative test, for sure this is positive, right? It's always positive. For this case, it's always positive. Why? 6 pi is positive. This is positive number, positive. And radius must be positive, right? So this whole thing is always minimum, right? What means that if you check also, any value of r here, we're giving you that greater than 0. So especially this one. This one is special a bit because why? This is a stationary point. And you're substituting here. And then you're getting a number greater than 0, right? Positive, greater than 0. So it means that r equals to 4 is the minimum point. So it means that find the minimum value of the total surface area. They want to find the minimum area. So it means that you have to find the minimum area here. So you know r equals to 4 will give you minimum area. So you substitute inside here. So 3 pi 4 to the power of 2 plus with 384 pi over with r. R is 4, right? So you're getting 3 times 16, you have 48 pi. And 384 divided by 4, you have 96 pi. Overall, therefore, your minimum value of the total surface area is equals to 48 plus with 96, which give you 144 pi centimeter, right? Even centimeter square, right? This is the minimum total surface area. After calculated, this will be your minimum total surface area for that container. All right. So now, okay, I have already teach you how. First, you must able to find the function that relate the area to radius or to height here. But for this case here, they want you to show that this will be everything in terms of r. So mean that you're going to replace the h, and you have to find the relationship between h and r, right? And later you differentiate the function, and you're getting first derivative and second derivative. So then you find the first derivative, then you equate to 0, then you're getting the optimum value here, the relative extremum here. But you know this is minimum or maximum, so you perform the second derivative test, so you get the positive value. So very sure this will give you the minimum value of the surface area. Then you're substituting this value into the area, then you are getting that minimum area here. Alright, I think that's all for this video.